All right. Hello, everybody. Welcome to my final project presentation, I guess you would say, for Astro 250. Today, I'm going to be presenting a package that I wrote over the span of the whole semester. Um, and I packaged it and added a bunch of stuff to make it like pip installable as well as reliable and have good code coverage. It was for my research. I was working on the code throughout the semester, and I was working alongside the entire like course, and like every time we learned like a new tool for like packaging, I would work on this. And event this is like the amalgamation of all of everything I've learned in the course through parallel processing as well as testing and packaging. So I'll walk you through my code. So I'm going to share my screen and you should be able to see um, this GitHub website. This is the package. It's called Cerebon. This is the logo I designed. The red, white, and blue scheme will be apparent soon, and the 3/4 will be made apparent in just a second. What this package is doing is it's measuring 3 and 4 point correlation functions of discrete periodic data in like n log n time. This is done using fast Fourier transforms. So for those that don't know what a point correlation function is, I think the easiest way to explain it is starting with a 2 point and then building up. So imagine you have a box of galaxies, and in this box of like in this giant volume of space, this three-dimensional box, you have these like point particles just representing galaxies scoured throughout. You might want to understand how these galaxies are separated, like what is like the most likely separation scale between these galaxies, and just like trying to find some information about how the structure is forming. Small scale structure, large scale structure. Do we see a lot of correlation between like in groups of galaxies, small clusters of them, or do we see no correlation at all? The way you would do this with the simplest way to do this is with a 2 point correlation function. So you take an anchor point and you allow this anchor point to go to each one of the galaxies, or these like points in the entire box. You pick an anchor point, and then you take your second point, so your second point, and you draw like basically a radius r between the anchor point and the second point, and you create a spherical shell at that radius, and you add up all the galaxies in that spherical shell. With that, once you've added all that contribution up, you do it again for all the different possible combinations of that anchor point with all the other galaxies, and you add up all these spherical shell contributions of all. Every time a galaxy falls in a spherical shell, you add it up, and then you average over all the possible combinations of that. So you pick another anchor point, repeat, another anchor point, repeat, and you can imagine that this scales like an n² problem, because you have to have two nested for loops, iterating over all the possible combinations. N² is not great, but it is doable, at least with semi-large data sets. But if you have 3 or 4 points instead of just 2, let's say you wanted to capture more of the angular information than just the spherical distance, or like the distances between, then you would need to create triangles instead. So you have an anchor point, and then you get 2 other galaxies, and you can draw 2 different side lengths of different length, and construct a triangle with that. And you have some angle and 2 side lengths, or 3 side lengths. And now that becomes like an n to the cube problem, n to the 4th, and so on. So what this code does is it measures it in n log n time. It measures the 4-point correlation function, which is normally an n to the 4th algorithm. The way we do this is it's a bit complicated to explain all the nitty-gritty details, but in essence, we have 2 ways to speed it up. The first of which is to say, instead of needing all the sides of your triangles or your tetrahedrons for a 4-point correlation function where you have 3 radial like this lengths on top of an anchor point, instead what we do is we use our like high school geometry to say, instead of side side side, why don't I capture all the information with side angle side? Except now I can decompose this angle by projecting radial coefficients onto an orthonormal angular basis. So what that allows us to do is truncate to an order. It's like a glorified Taylor expansion, if you think about it. So we cut the leading order to maybe 3 or 4, and now this becomes like an n² problem, no matter what, which is pretty cool. And then and you could do this for all the angles. So no matter how many sides you add, you only have to deal with, like, you eliminate however many degrees of freedom are available in your problem by truncating the angles. So for a 3-point correlation function, you have one angle that removes 1 degree of freedom. 4-point correlation function, you have 1, 2, 3 angles, or 2 angles, and that brings it back down to n squared, and so on, 5 point, 6 point, whatever. And then to speed that up even further, we use fast Fourier transforms to calculate all those coefficients at the same time by doing convolutions and whatnot. The nitty-gritty details can be found in my paper that will be released sometime this summer, hopefully, if you're curious. But that's the general idea. Sorry for a lot of explanation, but I feel like this doesn't make any sense whatsoever if I don't give some background explanation. So the way you use this package is pretty simple. You just import the package, and then you create like an MPCF object. So, and you call that by Sarabond.measure, where you give it some keyword arguments. Those arguments are listed below. And then Sarabond.calcZeta calculates the endpoint correlation function you want. So you give it whether or not it's a 3 or a 4, because my code only measures 3 and 4-point correlation functions. And then another key argument would be projected, whether or not you're looking at a 3-dimensional volume or projected onto a 2-dimensional plane. These are handled differently. So in total, I have 4 different algorithms running, or 8, but four pathways. And then a bunch of different arguments, like what directory do you want to save your intermediate files in? Like what is the density field you're going to put in, and so on. How many bins do you want? How many radial bins do you want to use? Spacing, a bunch of other stuff that's probably not super interesting for the context of the project. But this is kind of the pathway. So you import Sarabond, and then it walks you through the processes of calculating these 3 and 4-point correlation functions. So if you're using a volume, like a full volume, then you would take the top pathway and either go to 3 or 4-point correlation function. Or if you're using a 2-dimensional sheet, then you go through the bottom row, and you can split off into projected 3 and 4-point correlation functions. And a caveat, the reason, or one of the assumptions made by my code is that your data volume is periodic in nature. So you shouldn't be using my code to measure 3 or 4-point correlation functions on non-periodic data, meaning like it should kind of loop on itself. This is a common feature in simulation codes. So the whole point of this project was motivated to measure the 3 or 4-point correlation functions on non-discrete or non-particle data of galaxies, but for like simulations of the interstellar medium, which hasn't really been done before. So that's the whole point of my project. And you'll see kind of an example data set that we'll use in the demo. So walking through the the repository, I have a bunch of Scratchwork notebooks, testing, etc., images. But you'll see we have 91% coverage on CodeCov, which is great. And it's uploaded to PyPI. Right now I'm on 0.1 beta. Hopefully I'll be able to get it to like 0. Or like 1.0 by the end of the summer. There's still a lot of like nitty-gritty details I need to work out and like ways to augment it. I've done as much as I can in the time of this semester, but there are future plans to also allow this to go to higher order correlation functions possibly. So right now this is the state of the project though. Dependencies are really simple. I'm pretty sure the requirements is just NumPy and PyTest. So it's a pretty low level package in the sense that it doesn't really require much else. I believe any other like sub packages that I use are part of the standard default Python library, like concurrent futures and so on. So at least that's what PyPI told me. It wouldn't let me add those requirements. So these are like the main requirements needed, as long as you have like IPython or Python installed, is just NumPy, which is pretty cool. So the code is in the Sarabond folder. I have tests. I have both unit tests and integration tests. And I have several different files that run the code. None of this is super important, but we have several different approaches. This was me like debugging and whatnot. The full PCF parallel is the one that is like the one that the code is using. And You'll see there's a lot of code going on here. And I use parallel processing to make this algorithm go much faster. So what it does is it creates a bunch of intermediate files for all different kinds of combinations of bin and angular index and so on. And it does this to reduce the usage of RAM. Normally this can take up to like tens or hundreds of gigabytes, depending on how big and how high resolution your measurements are going to be. And so the way to keep everything in RAM, the code running, is to offload all these files into like a temporary directory and keep that keep that running and just pulling in files as onto disk as needed or into RAM as needed. And that way, basically what I did was I broke it up into a multi-process system with concurrent futures so that it can be run on a cluster or whatever, and it automatically assumes it takes into account what hardware you're using, and it scales appropriately. And so far, we see really good scaling with this code, which is awesome. Yeah, so that is kind of like a bit of the structure of this repository. Also, I'd like to add, I wrote the workflow so that whenever I make changes to the GitHub, it automatically runs the testing over again. It does auto testing and changes the code percentage. So when it'll also let me know if it failed, any tests when I use my integration tests and whatnot. So it's pretty robust right now to editing and changing and stuff. And we can also look at PyPI. Oh, that's a sticker, my bad. If you want to see the package on PyPI, it is pip installable. So if you go to PyPI and look up Sarabond, it's right here, 0.1.0. This is my code. Take a look, and you can go to the source code, and it'll take you all the way back to the GitHub. You just simple pip install Sarabond, and just to make sure that it works, I'm going to go onto the Astro Data Hub, which I don't believe I've used Sarabond on. We go to the Astro thing, and we open up a new notebook. Font 3. We can pip install Sarabond. Cool. So we installed Sarabond. We'll restart the kernel just to make sure that there's no weird behavior. Now I need to import all the necessary packages to to use the code in workflow. So the code itself only depends on NumPy, but if you want to actually understand what's going on, typically you're going to want to make plots and whatnot. So I have an application example in the notebooks that kind of walks through how to use it. So I'm just going to go ahead and copy this right over. We're just going to load in some data. So first we got to have a standard preamble. Oh, we don't need this. It's not necessary. That's for my custom style sheet. Cool. So we just imported things like NumPy, matplotlib, some sub stuff, OS, AstroPy, because I'm going to read in some data. Now I need some data. So I'm going to upload a new file. If I go to my computer and I go to desktop, and I think it's in package testing. Yeah, package testing. Sarabond. There's a sample data file in data. So if you go to dense t800.fitsgz, this is like the sample data that we work with. It's a fairly large upload, but it should be fine. Cool. So now that is right here. It's a fits file. And to read that in, we will need to, you could just copy right here using AstroPy functions to load in the data. It's going to be in this directory, so we don't need the data, subdata. What we do is we're going to take a small subset just for the sake of fast computation. It's a 256 cubed box, but we're going to just take an eighth of that box, so the 128 cubed, and then we're going to subtract off the mean just so that there's no so that when we look at correlations, it's correlations relative to random. Then we can plot the data. It's going to look like this. So if we go ahead and just plot, should look like this. So this is a slice of the density field, x-axis, y-axis. This is no physical units, it's just cells. And this is density, I believe we're plotting. And it's arbitrary density units. What matters though is that it's a volume. So it's a three-dimensional volume. If we want, we can do the projected and just take a slice of it, or sum like stack across an entire axis, and then we just have like a projected field. But nonetheless, this is like what kind of data it takes in. This is periodic data. It doesn't appear truly periodic because we're not looking at the full data set. If we were to look at the full data, you would see periodic behavior looping in on itself as it goes around. But for the sake of speeding up the calculations for this demonstration, we're just going to take a small subset. It's not going to be accurate coefficients that we're going to be measuring. So take these with a grain of salt. It's just for speed in the sake of our run. So if we want to measure the full 3 PCF, it works like this. You just, we have like a save directory, and then we want to get the current working directory, and then we can just make an output folder beforehand. So what I'm going to do is make an output folder before that in the directory. So if I go to new folder, there we go, yeah, and then we rename it to output. Cool. So now we have an output folder that we can put our temporary files into. We're going to feed it some keywords, like we give it the save directory, save name. We want 5 radial bins. Lmax is like the angular order of which we want to go up to. So Lmax of 1 is like first order, 0 is 0th order, 2 is second order, so on. It scales pretty poorly with higher Lmax. So between every Lmax, you get vastly many more combinations it has to loop through, which is a small downside, but it is the cost you pay for higher order calculations, or finer angular resolution. So yeah, this is everything. I just need to make sure I import the Cerebon package. So if we go ahead and import Cerebon, and we go ahead and run this, it'll start preparing the data, creating XYZ grids for radial bin, YLM. So this is going through like that diagram that we saw in the GitHub repo. This is the full 3 PCF we're looking at. It creates a bunch of spherical harmonic bins files. It's not super important how all these work, but it creates these in that temporary output directory folder. And then it calculates these things called ALM coefficients, which depend on these spherical harmonic coefficients and their kernels and whatnot. And then once it goes ahead and creates all these ALM coefficients, it returns the 3 PCF to this or it gives this attribute to the 3 PCF object. So if we want to go ahead and take a look at the zeta, we can go ahead and plot 3PCF.zeta. So what this will look like, this will be for the 3-point correlation function. It'll be 3-dimensional. It'll be a 3-dimensional array where like the 0th index refers to angular resolution, and the first and second indices refer to the bins. So this is angular order, and these are like your radial bins. So we're only looking at the first 4 radial bins, and you can see it looks like this. So these are coefficients. This is not the actual density field, but it is the coefficients. density field. Now, the 4-point correlation function is going to take a lot longer, so we're going to skip that. But for this, and I'll come back to that towards the end. But if we want to look at the projected 3 PCF or the projected, yeah, see so in this example, the full 4-point correlation function will take almost a minute to run. So we're just going to skip that for now. But it'll give you an output that looks like this, where we have now it's 6-dimensional because we have 3 angular orders for 3 different angles in our tetrahedron, and then 3 side length bins. So it gets drastically more complicated. So for the 3-point correlation function had 2 radial bins or R sides and 1 angle. So it was only 3-dimensional, but now this is 6-dimensional. And if you had a 5-point correlation function, it only gets worse from there. So we look at slices along one of the radial bin coefficients, and we're looking at like mostly first order contributions in this angular pair. The details are really confusing, but this is what the typical output would look like. And then this is like the 3 and 4-point correlation functions coefficients for the same data set. Now, if we want to do projected, it's a little different. We need to take a slice of the data. So the good thing is the projected versions are significantly faster than the full because they're only looking at 2-dimensional data, so it's a lot less data to work with. But we're just going to take a small slice out of this data to turn it into a 2-dimensional data set. And if we go ahead and run this, you see it already finished in like 0.5 seconds. And we can take a look. Keep in mind, we're going to 20 radial bins instead of 5, for example. So this is significantly faster. And when we look at what this data looks like, it's going to give us real and imaginary coefficients just due to the way of how the function works in 2-dimensional space. We can plot the real and imaginary parts. So white refers to pure randomness, and red refers to excess of correlation, and blue refers to deficit of correlation relative to random. So you can see some interesting structure going on here, creating these kind of like lobes in this angular space. We're looking at an angular order of 2 in the projected space. Instead of L, we use M for various reasons, not super important, but it measures these coefficients from the code. And with these coefficients, you can use them to do things like classify like different simulations of the interstellar medium, for example. This was in a paper done by Andrew Sajari et al. Like a year or 2 ago with a 3-point correlation function, but mine measures 3 and 4-point correlation functions. And a potential thing we want to look into is classification of these simulations using the results of this code. These coefficients can be used for classification purposes, which is really interesting. And then lastly, the final bit is the projected for PCF. We could give it on the same data set, the same like like input data, go to 20 bins, and it'll take a little bit longer, but still only takes on order a few seconds. I believe, let's see, it should take, this will take 40 seconds. We can reduce the, well, I guess it's fine. I could keep talking while it runs. Yeah, and the further like direction of this project is going to be to use this code to measure 3 and 4-point correlation functions on the interstellar medium, use them for classification schemes, use them for possible analytical models that we can understand a little, or try to probe a little bit more of turbulence in the interstellar medium. So trying to understand things like the Kardashev scale of turbulence like and whatnot, and like the power spectrum and whatnot. Interesting ideas that my advisor and I want to look into. He's normally a cosmologist. I'm interested in simulations, so it's kind of like a happy medium. And now that this is done, we can look at the data. So this is going to be a bit more, it's going to be a bit more data to look at, or a bit more complicated to explain. But again, we take the real and imaginary part. We have, in this case, there's 3 potential R's, so or radial bin indices. So we only look at a small, like a slice of them. We're looking at like the R3 is 0, for example. We're plotting R1 versus or R2 versus R1. And again, white is random, red is excess of correlation, blue is deficit of correlation. You can see some interesting structure forming here. And again, or like we only have 2 angular degrees of freedom and 1 and 2 because of the the symmetry of the, or like because of the behavior of 2-dimensional math for this problem. You can cancel out the third angular dependence and use an identity for that. So that's pretty cool. I think that's just about everything about my code. I can run the full 4-point correlation function, but it'll take a minute or 2, and I don't think that's a good use of your time. So if you're curious, it's in this notebook. I mean, I just copied straight from this notebook, so anything that runs in this notebook will run in that other code. I guess one last thing I should mention that might be confusing. Sorry, I used a bad color map for this 3 PCF. Usually I use red and blue, but I forgot to change that. I can change that in a second. But you'll notice the middle is diagonal, or the diagonal is white. Sorry, and the reason for that is it doesn't make sense to look at correlation with it's with itself. So we use this to remove any self-correlating factors between the R's. So it doesn't make sense to look at the same R1 and R2 when they're exactly the same length, because then you're like kind of getting like unnecessary addition to the field. It doesn't make sense. So we don't do that. But and you'll notice for the 4 PCF, you'll notice these like white line, the same kind of white lines along the 0 axis, and this is because we're looking at the 0, 3 third index. So it's giving this kind of like, it's doing the same effect as the diagonal, just with the 3rd dimension. It's a bit confusing. I apologize if this is not the easiest thing to understand. If you're interested, there'll be more information about this in my paper, and it'll be far better explained than in this short little demonstration of my code. But the main takeaways are I packaged the code. It's pip installable, just pip install Cerebond. It should work straightforwardly. You can run the notebook if you want. You could clone the repo or download the data that I used. This is just a simple, like the input data is really the equivalent of just like a 3-dimensional NumPy array. So you can make it like random. You could just populate a 3-dimensional array with random numbers and it would work just fine. It wouldn't mean anything because the data needs to be periodic for it to actually mean anything. But nonetheless, the code process still works. It works by creating a bunch of temporary files and offloading them into a directory, and then only importing them as needed into RAM. That way we can run big computations very memory efficiently. And then I use multiprocessing in the concurrent futures module to split up the loading of these files into different subprocesses. So for every one of these lines is a different file, for example. So if there's like 20 or 30 files and I have 4 processes, it would make sense to not load them in serially, because all they need to do is just be summed and added with a couple factors and stuff going on. But the main process is just summing up all the contributions. So we could just sum these all up in parallel and then stack them. So I have several different processes summing or pulling in a few of these, a few of the subs, like a subset of each directory's files, and working with them, and that drastically improves the computational time. For example, without the multiprocessing, this was on my laptop with 4 cores. This was a factor of 4 bigger. So this would, instead of 50 seconds, it would have taken 200 seconds, and so on. So and I already tested it on a supercomputer like HyperGator up at University of Florida, and we see drastically faster code improvement. I use 16 cores, for example, and I got a factor of 16 increase roughly. So it's pretty exciting. The parallel processing features that we covered in the course really helped to speed it up. And I have code cove testing. My unit tests look like this. They could be found in the test folder. I have several unit tests for just like bad data shape, box size, mismatching data, like your Mmax, Lmax. There could just still be a lot more tests to be run, but I already have 91% code coverage, so I felt like this was pretty sufficient. And then I have all like integration tests for all of the pathways to make sure that they don't fail. And so that's pretty good. And then, yeah, I think that's everything to say about my code. I can't think of anything else to discuss. So I hope you enjoyed this demonstration. And yeah, thank you for teaching me everything. I really appreciate it. It was super helpful for this course.